Yeah, thank you. And thank you for sticking with me until the end of the session. I'm very happy to present and conclude the session with this paper on slate generation. And so the goal here is to recommend multiple items as a coherent group, right? So as a slate, we mean a collection of items. And so often we think about, for example, best tracks that match a prompt, a content hypothesis. But in this case, we want actually to create a best playlist, a best collection of tracks. So besides music playlists, you can also think about like bundles in e-commerce, right? Where the user is experiencing all the items at the same time. But that's also why we think about playlists in this way. It's not only like a collection of items. We care about like how the tracks relate to each other as well. And so, of course, the challenges include the combinatorial nature of the problem, the consumption, and the structural coherence. But why it matters is because, yeah, we go beyond individual item ranking, right? We focus on the collective quality. And also, we try to enable discovery of new, but at the same time, relevant content. And this, of course, has lots of implications for our users. So we try to reduce the friction of trying to, for example, curate their own playlists, but also enable, again, as I mentioned, discovery and to engage for the content recommendation. And in music, the flow matters, as I mentioned. It's not only the best single tracks, but it's also how the tracks are organized that matters. And so this is why we use the diffusion models for slate generation. So diffusion models are great to model high-dimensional structural patterns, right? And so the idea is that they generate relevant and diverse slates, and in this case, from some conditioning, I would say, which in this case could be like natural language prompts. But also they provide a scalable and low-latency solution, as I will talk about in a minute. And the interesting bit that I don't have time to go into too many details now, but using continuous diffusion models, we are able to separate this discrete problem where to select the single tracks by using a continuous diffusion models, and in such a way that we don't have to retrain the model every time a new content comes in. So a little bit about the methodology is the only important bit to remember here is that we have these two parts that the diffusion model sees about the playlist, which is the conditioning label and the item embeddings, right? And so essentially what the diffusion model is doing is trying to replicate the embeddings of the playlist using the conditioning mechanism. And this is very nice because at generation phase, it means that using only the conditioning mechanism, so in this case, textual prompt, but here I also mentioned additional item embeddings or such kind of additional conditioning, we are able to generate a list of latent vectors that we are able to map as a separate step to the actual tracks, to the actual playlist that we want to generate. And so in terms of the experiments, we focus essentially on two main aspects, right? So one is relevance. So are we actually recommending relevant tracks based on the conditioning? And I cannot go into too many details, of course, but we are able to see and map how the model can actually select like relevant items. But also something that are very much interested in is this exploration and freshness, right? Because we have like so many ways to actually map the best content. We know the best tracks for the user, but what we also would like to have is to enable the user, especially to explore and discover maybe the new tracks that may be like very relevant for them, but they have no way of finding. And so we do see that for example, in this case, we have like the item popularity, which is like decreasing using the diffusion model, but at the same time, increasing the relevance. And every time, so due to the stochasticity of the model, we see how at every time we ask the model to generate a new slate, we have like this fresh content at every step of the way. And interesting, we also evaluate it online using through a 2 weeks A/B test on a production Spotify music playlist generation system at scale. So we were able to implement it at scale with no issue at all in terms of latency, and especially we were looking at these two metrics, right? Stream curations, so how much the user were actually engaging with the new content, and the listening behavior, so how much, for example, the minutes were played and the skip rate and so on. And the online results were super promising. So especially for existing and habitual users, we did see a 6.8% on overall uplift in stream curations. So users were actually engaging more actively with the tracks recommended. So stream curation meaning, again, adding to their playlists or adding to like songs. And we did see a reduction in repeated tracks served to the same user, 13%, compared to the control group, meaning that new tracks were served to the users, and they were actually able to engage a lot more with them. So to conclude, we tried the diffusion models, and we show how the structure and coherent items that they build are actually meaningful, are actually relevant, and are able to scale to the Spotify online use case, especially enabling us to balance the content freshness with relevance. Using the only other thing that I wanted to mention is the next step. So I also mentioned the conditioning mechanism that we use is mostly based on natural language, but we could add additional like personalization components just by using like more the conditioning mechanism that diffusion models are naturally like allowing, I would say. And thank you for the attention.
I have a question about, so your model based on a text prompt, you generate these latent vectors, then you map them to the items. I assume this is some like sort of nearest neighbor search, but I'm interested in the latent vectors themselves. Have you looked into what they look like? Like, do they neatly map to the items? Or do you sometimes get things like, oh, actually, there's this point in the space where we would actually like to have content, but we don't have it. Like, is that something you've been looking at, or?
Absolutely, yeah, absolutely. And that's exactly as you mentioned, like it also depends, like it depends a lot on the prompt, like on the conditioning mechanism. And so it may happen that in part of the space, because the space of course depends on the training data, right? And so the more training data that you pass, the more playlists that we have for the model to learn on, like the more dense the latent space of the model can learn. And so there are cases where, for example, I didn't go into details, but for example, we train the model mainly on editorial playlists that we have at Spotify, and so those are mainly about genres. And so for prompting that are maybe like a little bit more nuanced, it may be like go into some part of the space where the model didn't see the like many tracks of the catalog. Yes. And so in those cases, like additional, this is also why like this separate catalog mapping is very important, so that we are able to still incorporate like additional knowledge about that we have about the users, about the catalog to correct where the diffusion model is not like on point, I would say. Okay.